Welcome everyone to the November 2018 Soils Network of Knowledge webinar. There's been an incredible amount of interest in this topic with our speaker today, who is the Soils Unit's newest member, Jason Condon. He is currently a Senior Research Fellow in Soils at the Graham Centre for Agricultural Innovation, which is a position that is co-funded by Charles Sturt University and New South Wales DPI. Prior to this, Jason was Senior Lecturer in Soil Science at Charles Sturt University at the Wagga campus, where he taught soil science and soil management students studying agriculture science, horticulture and wine science. His research covers issues of acidification in crop and pasture systems, subsoil amelioration strategies and soil nutrition, including nitrogen, phosphorus and carbon. And today he's going to talk to us about soil acidity and what the new understanding of it means for this issue for soils and its management.
Thanks very much, Abby. Okay, so welcome everyone. I'm going to talk about soil acidity today, and I thought I'd start by just looking at where we've come from a bit, because I think it informs how we tend to view soil acidity, and sometimes that's not overly helpful moving forward. So we'll just start at the beginning from an Australian point of view. I'm largely focusing on a New South Wales point of view as well, understanding that things are a little bit different in the West with their sandy soils. So we know full well that agriculture acidifies soils, and I just want to show some data here by Williams. So we've got on our y-axis here soil pH and years since pasture was established, a sub-clover pasture, from 0 right up to 50. And what has basically happened is over that time, soil acidifies due to agricultural production. Why I've chose this set of data is because it actually includes a bunch of work that was done in the 40s and 50s, and then continued on into the 70s. In the literature, acidification or the presence of acid soils in Australia, you sort of see in the 1930s, but this is a really nice set of data to show that our agricultural practice is acidifying the soil. And that acidity then limits production. And we know from a bunch of research internationally and also in Australia, most of that limitation of production is tied up with aluminium and manganese toxicities, which will harm the plants. You can get, when you have a lot of aluminium in the soil, you can then get leaching of other cation nutrients like magnesium and potassium. So they leave the topsoil, and then you get deficiencies of those. They're still in the profile though, but just the establishing plant struggles to get them because those nutrients have leached lower down. And of course, acidity affects the availability of both phosphate and molybdenum. So in an acid soil, you can get deficiencies of those things as well. So this soil acidification actually around in New South Wales first presented as a real problem in yellowing of wheat, and it looked like waterlogged soil, you know, that classic yellowing in waterlogged soil, but the soil wasn't waterlogged, and that's when the investigations around in the Wagga area started identifying soil acidity as a major limitation. And of course, if you had yellowing wheat, you'd start thinking, I've got a nitrogen problem, but that wasn't the problem at all. So given that agriculture acidifies the soil, acidity is then starting to limit that production. We needed to understand what causes that acidification. And so a lot of work was done in the 60s and 70s, and using theoretical models, we could start to develop an understanding about what was driving acidification. And there's some classic work in the 70s by Keith Hellier, and then which involved nitrogen modeling, and then Hellier and Porter later on then included organic matter components. And so you develop this theoretical model and this is a sort of a modern updated version of the same thing. But you know, there's nitrogen components and there's organic components here, and we understand each of these processes has an effect on soil pH, which is all about the hydrogen ion concentration. The more hydrogen ions you have, of course, the lower the pH is. And so these theoretical models allowed us to understand what was creating the acidification, that decrease in pH. These models were then used to estimate the alkali, or the lime, if you like, required to balance that acidification. And so basically using those models, you could say, right, if I've got a product, be it cereal hay or grain, then if those processes that we understand in those models work, then for every ton of product, you should have a certain number of kilograms of lime that you'd have to use to neutralize the acidity that created when you take away grain or take away hay. So these were calculated using those models, and then in some experiments were also ground truth, if you like. So that's product removal. Use of fertilizers were also looked at. So when you use those models and you've got, say, monoammonium phosphate fertilizer, then the processes that occur there, for every kilogram of nitrogen used, there's going to be a certain number of kilograms of lime that you'd have to apply to neutralize that theoretical acidity. And I say theoretical acidity because that's what it is. This is all based on those, generated from those models. And so if you look at urea, for every kilogram of nitrogen, in theory, there is no change in pH, and so you don't need to add lime to neutralize that acidity. So I will come back to that, so I want you to remember that. So the models would say that urea doesn't necessarily acidify. The problem is that those models operate on a profile basis, and so theoretical models create theoretical outcomes, and therefore they also create theoretical solutions, and that's fine. The idea of a model is to create an understanding, to create theoretical outcomes, which you can then test. The problem is when people don't realize that they're theoretical and they just run with it, you can come unstuck. To give you an example, so we know that ammonium can convert to nitrate by nitrification process, and that's acidifying. So normal process, nitrate's created, acid is produced. If that nitrate's taken up by plant, then theoretically an alkali is released back into the soil. And so what happens is some of that, well, that alkali will then neutralize some of that acid formed by the nitrate production. So that's theoretically, that's how things can work. And of course, then taking the next step, that same process, if that nitrate is actually removed by leaching, then the plant uptake part, this alkali part, doesn't occur. And so you're just left with acid. So theoretically, if you had nitrate leaching, you don't get the alkali produced and you get the acid remaining. And so the problem was nitrate leaching causes acidity, and therefore the solution is we'll have deep-rooted plants to capture the leached nitrate, and then you'll neutralize some of that acidity because the alkali is formed. So that's the theoretical. But the problem is, the question is, where did the acidity occur and where was the nitrate taken up? So this ammonium is either coming from fertilizer addition or from the breakdown of organic matter, which happens in the soil surface up here. So that's where the nitrate's formed. That's where the acid is produced, and the acid will stay. And then the nitrate leaches and is taken up in the subsoil, and that's where the alkali will be released by the plant. And so even if you get uptake of nitrate, you'll still acidify the surface soil. So these models, which the theoretical models, don't actually account for movement of things within the profile. Another example for you, urea, fertilizer, converts to ammonium by a process which increases the pH. That ammonium can then nitrify, as we've just shown, and that's quite an acidifying reaction. And if that nitrate's taken up by a plant, as you know, that you get an alkali release, And so we've got an alkali, two acids and an alkali, you add them all together and you'll get no pH change. So this is where in that Cregan and Hellyer table, which I showed you before, urea needs no, for every kilogram of nitrogen that you apply using urea, you don't need to add lime because theoretically there's no pH change. We did an experiment here where we had, there's a pot trial, we had 30 centimeter pots, measured pH, and we had a control which had nothing added to it, and we had urea added, and that urea was banded at a depth of 13 centimeters, so like a pre-sowing deep banding operation, 100 kilos of N as urea, banded at 13 centimeters. And initially the soil pH, wasn't acid, and it was the same all the way through. And we let that urea sit in the soil for 4 weeks. Then we sowed barley into it, and we grew that barley for 8 weeks. And then we came back and sampled the soil. So here we have our pot with pH. And this was the story after 8 weeks of growth. Our control was pretty much the whole profile acidified a little bit, but relative to the urea actually acidified the soil a lot, significantly so, and it's quite acid. Now, it's acid. This is 4 centimeters off the urea band, so horizontally 4 centimeters away from where that fertilizer row was, we've actually got acidification occurring. And so after these 8 weeks, all the nitrate was taken up, all the nitrogen that we applied was accounted for, but we've left with acidity. So whilst the theoretical model would say that there's no pH change if all of the urea is taken up by the plant, or is utilized by the plant, then there should be no pH change. In reality, we do get this acidity, and it's because these nitrogen forms all move. And in this case, it's moved horizontally and it's moved upwards and downwards, and then reactions take place which are acidifying, and so it acidifies the soil. So acidity is a problem, and it's made worse by agriculture. We understand that. You can't get away from that. The whole practice of agriculture will acidify the soil. That food production or fiber production, consequent society benefits, farmer gets money ideally, but the soil will acidify. The causes are really well understood, and that's thanks to the modelling that's been done. Those Hellyer and Porter type models have allowed us to understand how this happens. But soils aren't a bucket, and so we can't think of soil as this one-dimensional thing where we add acid due to our agricultural practices, we can add alkali, lime, and therefore we can balance pH. It doesn't really work, and that's because we can't manage the soil as if it's a bucket, because it's a profile. It has layers, and different processes happen at different parts of that profile with depth, and therefore the consequence of those processes represent themselves at different depths. So the pH changes at different depths. So we need to stop thinking as the soil as just one bucket or a unit. So what do you do with that? How do you manage that? It's not a bucket, it's a profile. So we need to actually measure the pH in that profile. So in the measurement of pH, we need to understand, firstly, it's a really highly variable property. And that variation occurs sometimes due to soil type, sometimes the influence of plants, the influence of management practice as well, but hugely variable. To give you an idea of that, let's have a look at these things. So what we've got here is pH of a soil grid. So if you're looking down on top of this thing, imagine this being on the ground, and it's just 10 centimeters by 10 centimeters, and it's a grid. So wherever you draw lines across every centimeter, this axis and this axis, if you measured pH at every centimeter, this is what you end up with. And so we've got a scale along here. 6 is blue, 4 is red, you get a variation. So this is a 10 centimeter by 10 centimeter square. So there's heaps of variation there. 10 meters by, oh sorry, that's 1 meter by 1 meter. So each of those are 10 centimeters. And this is 10 meters by 10 meters. Variation again, 100 meters by 100 meters. So you've got similar amounts of variation at these different scales. And things like stock urine patches will change pH dramatically. And so we all know, you can imagine a mob of sheep walking through a paddock doing the things that they do, how that's going to create variable pH really quickly. So what do you do with that information? Well, if you want to know what the soil pH is, take a lot of samples. And you reach a point where if you don't take enough, you get such variation between your measuring points, sampling points, that it's just noise. The numbers that you get back don't mean anything. But you can go too far. You can take a heap of samples and you don't actually get much return for that extra sampling. And so statistically speaking, about 25 to 30 samples of the area that you're interested in will give you the best estimate of the true mean without ridiculous amounts of noise. And if you go more than 30, you don't get a lot, you don't get a greater precision for that extra effort. So 30 is a good number. Now, I said of the area of interest. And so whether that's a meter by meter area or whether it's a hectare, if this was, I want to know what the average pH was in here, then that'd be 25 to 30 samples you would take. And of course, you're going to hit potentially, it'd be random where you get, and that's why you take so many samples. Now, we might talk about sampling a little bit later on as well, but there are a whole new tools available that we can measure areas, whether it's grid sampling or not. There's just different techniques coming online now, but I just want to stress it's the area that you're interested in. And I think a bit of knowledge of soils, you can actually pick where you're going to have differences in soils, where you'd expect there to be differences in pHs, and then you can start treating those areas as separate areas using these sorts of numbers, sampling within them, to get the sort of useful numbers that you can then manage with. But you've got to measure, which means you've got to sample. Now, so it's highly variable. Take a lot of samples of the area of which you're interested in. Now that's just subsamples. So you could take 30 cores and bulk them into one sample, and then you actually get one analysis, or you can group sample and get actual 30 numbers and get 30 samples, send them off to the lab. But there's an extra cost there. And the question is, how much extra information do you need to make a sensible management decision? That's an open question. Right, so the thing that we're measuring is variable, and then, because life's never easy, what we measure is different. The actual measurements that we take can be different. So you can measure pH in water or calcium chloride or potassium chloride. You can measure it at different soil to solution ratios, and these extractants can have different concentrations as well. And all of those things will change the number that you get from that sample. The pH in the field is what it is, but what you're actually recording changes depending on how you measure pH. The aluminium, so the trivalent aluminium is the toxic stuff. The concentration of it can be measured by a range of different methods. That concentration can be expressed in different ways, as a concentration or as a percentage of the effective cation exchange capacity. So what you measure can be expressed different ways. None of those things are perfect. There's not one thing that you can say, it is this is the best thing to do. I don't know why everyone uses that other stuff. They're crazy. None of them are perfect. The strength of the relationship between some of these measures, like between calcium chloride and the concentration of trivalent aluminium, that relationship will vary. The strength of that relationship will vary depending on the soil type, the texture, how much organic matter is there, the clay minerals that are present. How those things relate to plant growth can also vary. And so this is why when you look through the literature, you know, for some soils, one test is better than another, but it's not necessarily massively better. It might be incrementally better. And so I don't lie awake at night worrying about what we're going to do with this, given that what we're measuring is highly variable in the first place. These things, it's just a measure. It's just something that we can use to record changes and try to relate to plant growth for our soils. And the best thing that we can do, soil practitioners, is actually measure pH in the soils that you're dealing with and monitor them through time to see how they change and how they relate to plant growth. For New South Wales, most of the research that was done has been developed on 0.01 molar calcium chloride, so the pH is measured in that, and aluminium percentage, the percentage of effective cation exchange capacity is what we tend to think about in terms of, are we getting to a harmful concentrate or a harmful value that's going to limit plant growth. And this is all based on 0 to 10 soil samples, because that's how the work was done. So our soil testing strategies that we use with farmers tends to be 0 to 10, and the numbers that we get back in these, measured in these ways, you can easily fit back and look back into the literature and find how they relate. But it's really important, just before we move on to another slide, when you measure pH or measure anything in soils, that you make sure that the methods that are used are known, so that, you know, if you're comparing values from 2018 to 2015 to 2008, that you're actually comparing apples with apples, the same units, the same methodology, because that's going to be the true measure in change. Now, in terms of liming, so we're going to measure pH and it gets to a low point. You think, right, it's too acidic, I need to lime. How much lime do I need? Models have been created based on experimental work, and lime, there's, I think, there's a third, it's lime at 3 is the last one. So they're based on experiments, but those experiments were used high quality lime, greater than 95% neutralizing value, in some cases it was 98%, and super fine lime, so ground to less than 250 micron in diameter, so super fine lime. And that lime was incorporated to 10 centimeters, or approximately 10 centimeters, and that was because the farming practice at the time involved cultivation, whether it was by disc or scarifier, before sowing. So you actually had quite a lot of mixing. So the research that was done in the 70s, 80s, that's how the effect of lime was examined using those practices. So whatever outcomes we now look forward into the future, and we're trying to fit back to what we know about liming rates, we need to understand that the work that was generated or done to identify these liming rates, what are the appropriate liming rates, this was how they created that information. This is how they created those, you know, the work that went into lime it, incorporating into 10 centimeters using superfine lime. So these models, it's a computer model, that's great. Simplified into a table for the purpose of extension, looks something like this. And so along here, we've got the lime required to lift pH in the top 10 centimeters. And we've got sort of blocked from starting points, different starting points, whether you start from 4 or 3, 4.3 or 4.7 to get to 5.2. Now, 5.2 was the target traditionally in the early work that was done with liming, because once you get over 5, you decrease the aluminium toxicity. So the major problems with acidity is actually you get rid of it once you get up over 5. So 5.2 is at the target, and that at the time there was a sort of a practical economic component of that as well, because if people didn't lime previously and you were trying to encourage them or show them what was possible, then you're kind of looking for your lowest cost option to get a beneficial change. And so that's why 5.2 was targeted. Along our in this column, the thing that changes how much lime you need for any starting point, which is ultimately a measure of the soil's buffering capacity, the soil's ability to resist pH change, when you add an acid or an alkali to it. And that buffering capacity is driven by things like the amount of clay that's there, the amount of organic matter that's there. The easiest measure, if you like, from a standard soil test that you can use to understand buffering capacity is the effective cation exchange capacity, because it sort of amalgamates the clay, the charge in the clay, and also organic matter, because the higher organic matter you have, the higher your cation exchange capacity will be, and that changes with pH too, though. But so basically here, as you go from 1, 2, 3, 4, 5, as we're going down these columns, our buffering capacity, pH buffering capacity, is increasing. Okay, so this is something that we can get from a soil test. Our initial pH we can get from a soil test, and so with those two numbers, then you can start calculating or estimating how much lime do I need to get up to 5.2. And then once you're at 5.2, if you wanted to go higher, this is how much you need to add again. So the lower the starting pH, the more lime you need. The higher the pH buffering capacity or amalgamation of, the more lime you need as well. Okay, so that, if you like, is there are a lot of rules of thumb come from that table in terms of our liming practices that when you talk to people about what they do and why they do it, comes from this table. Just going back, highlighting, incorporation, 10 centimeters superfine lime. Okay, so that's the practice. The problem is, since then, our agricultural systems have changed, and they've changed by changing the acidification rate. So things like we have canola now that people use a lot more nitrogen fertilizers to grow, and so you tend to have a higher acidification rate because of that. In some cases, people have gone to continual cropping. They've dropped legumes out of the system, and they're becoming highly reliant on, again, nitrogen fertilizer application, and that can acidify the soil, especially when you consider we're using precision placement techniques, so guidance systems which actually put the fertilizer in the same place every time we sow. So it's not like we're randomly allocating fertilizer across within the paddock. We're actually putting fertilizer in the same place because we can now, because we're putting our sowing rows in the same place every year or every second year, depending on how you actually do that. And so that's that precision placement. So you're actually getting, again, if you treated the soil as a bucket, it's not a problem, but we're not. We're actually concentrating the fertilizer in a band. So where your fertilizer band is, the acidification rate could be much higher than what we think currently, and certainly based on the models, what we would have thought based on the models. So our acidification rates have changed, and we probably need to do a bit more work to understand how much they're changed, how much have they changed, how quickly are they changing, and especially given some of these new technologies we have. The other big change is that we don't mix the soil as much anymore. So we, large, no-till's common, disc seeders are out there, and they just do not mix the soil much at all. So it's possible, if you're zero tilling, disc seeding, that your soil just doesn't turn. It doesn't get turned over. And where people are liming because they're really keen on maintaining the structure with their no-till practices, they resist going and incorporating lime into the soil because they don't want to do damage. I get that. But what you're effectively doing is liming without effective incorporation. And that is problematic. To give you an example of that, here we have depth down to 12 centimeters, and on our x-axis here we've got soil pH. And here's a profile, like this is a really common profile shape where it sits up and down on, left and right will depend on the soil. If you're in WA, this would stretch down a little bit further, but the shape is there. It's the same shape. So this is what we call pH stratification. The pH in the 0 to 10 is not a straight line, it's actually a curve, and we understand, we know the reasons why it does that. We understand that, but that's the reality. This is what you get. Now the problem is this: if you take a 0 to 10 soil core of that and mix it up and send off to a lab, the number that comes back is effectively an average across that coring depth, and in this case it would be 4.85. And you'd go, right, 4.85, maybe I want to broadcast lime, because I want to get that higher up, and you can have a debate. What is your trigger point? At what point do you say I'm going to lime? For the purpose of this discussion, I don't like acid soil, so I'm going to not let. I'm going at 4.85. I want to grow a sensitive crop in a couple of years' time, so I want to get my pH addressed. I want to get the aluminium out of the profile, so I'm going to lime. So if you broadcast lime on that and don't incorporate, what you do is just actually increase the pH in the surface where the lime is. And so you haven't actually changed the pH down here because the lime hasn't got there. You've put lime on the surface, it's increased the pH up here, maybe a little bit there, but all these are unchanged. So if we sow into this soil, the germinating seed has to grow through the most acid soil. If you took a 0 to 10 soil core, the pH is 5.25, and you'd sleep well at night knowing that your lime application has addressed the pH as you wanted it to do. You spent the money, or you sampled the soil, you spread the lime, you've got the difference you want, and you'd be really happy with that. And so this 0 to 10 masks the actual pH stratification that occurred. Just remember, if you incorporated that, if you actually mixed that in, so offset disc, for example, then this would actually look more like this straight line, and your 0 to 10 sample would actually be a true representation of what the pH is in that profile. But because the soil's not being mixed, the lime is not being incorporated in, the mean, the average of that 0 to 10 is not actually representing reality. Give you an example of the consequence of that. So went out to see some growers at Harden. We're in a paddock with wedge-tail wheat that was struggling, underperforming, was quite patchy, but didn't look healthy at all. We used a dig stick, which if you've not seen one before, think of it as a big solid piece of pipe with a slot cut in the side of it that you can bang into the ground and pull it out, and it gives you an exposed core of soil. And then we can use this colorimetric pH kit, which just puts a pH indicator over the soil, and then there's a white powder, barium sulfate, that you sprinkle on, and it sucks the pH indicator up into it, so you can then see the colors that change, and the color change depends on pH, which you use on this card. Now those kits, they're about less than 20 bucks from, let's call it Bunnings, and so it's a cheap thing. Dig stick costs a little bit, but it's worth having. Stuck the dig stick in, put the indicator on, had a look, and basically in the top 5 centimeters, the pH was around 6.5 and 7, and this is equivalent in pH measured in water. But after 5 centimeters, it was a yellow color, so the pH is less than 5 here, which would marry up to about 4.2, 4.3 in calcium chloride. So it's really acidic down here, and basically these plants didn't put many roots below below 5 centimeters. There was some, but not many. And so that was a real limitation to that crop. It also had quite a lot of rhizoctonia, and so the theory there is that when the plants are stressed by this soil acidity, by the pH stratification, they're more susceptible to disease then as well, which is a problem. Now that problem was not diagnosed by the standard 0 to 10 sample, because the 0 to 10 sample of this that was sent off to lab and came back said the pH was around 5 or a little bit above, and so it shouldn't have been a problem. But the reality was that this did have pH stratification, and there was severe acid lower down. So what do we do with that information? Well, perhaps we need to start thinking about looking at sampling at different depth intervals, so 0 to 5, 5 to 10, 10 to 15. Maybe we keep going. It depends what your soil is. So you have a look at this dig stick. Once you hit clay, and you start getting into the subsoil, and that subsoil is alkaline, then if you're chasing the effects of acidity, then you only really need to look at that topsoil component. So it's what depth do you go to depends on your soil, and you'll know your soil because you dug a hole in it and you know how far the topsoil goes before you hit the higher pH clay. So yeah, sampling in these depths, although it takes a little bit extra time, you get really, really useful information, especially if it's a sensitive crop that you're planning on growing. And I always argue that you don't go doing this testing to sow next year's sensitive crop. You want to be checking out the soil a couple of years beforehand, because if it is acid and it's a zone that you can do something about, then you need time for that management practice to actually take effect. The importance of this has really been highlighted by work that Helen Burns from DPI here in Wagga has done on a GRDC project looking at pulse crops, where she's identified this stratification is super common, largely because of our movement towards no-till, our not using incorporation when we put lime on the soil. And so we're getting, if you like, poor information from our 0 to 10 sampling. We're missing the story. Where farmers are liming, they're spending the money, they're putting the lime on, but it's up at the surface where the soil doesn't need it. Soil needs it down here. So the people that are spending money on lime but not incorporating it to then grow a sensitive crop are actually losing twice, because they've spent the money on the lime but they're not getting the benefit, and then they get hammered by the acidity that's still there anyway. So measuring with the appropriate depth increments would identify the problem. You'd then say, right, I need to lime and I need to incorporate that lime to get rid of this acidity, and then I can grow my sensitive crop and get the financial benefit from them. I should say too that this stratification being a problem in the pulse crops that Helen identified, first seen here down at, around Holbrook, where a faba bean crop was yellow. So it just was not behaving like a legume at all, which, if you remember back at the start, we first realized we had an acidity problem when the wheat started going yellow, because it couldn't get the nitrogen because the roots had basically been stunted by the aluminium. And now we're seeing our grain legumes showing us that they're not functioning as a legume because the roots are stunted, and the rhizobia can't actually create nodules because the roots are hammered by the aluminium. Right, so if you're not going to incorporate, what can you do? Here's some work done in the 80s, and basically we've got soil depth here down to 16 centimeters, soil pH along the top here, and this is soil pH after 5 years after an initial liming event at different rates. And this is work by Mark Conyers and Brendan Scott. And basically, they cultivated initially, when they put the lime on, they worked that lime in, incorporated it in to a depth of around about 8 centimeters. That's what this little I stands for, it's the depth of incorporation. And so 5 years later, where you didn't apply lime, you had this pH profile, and you'll identify that as a stratified profile. And again, research that was done in Wagga by a bunch of different people, we understand why this forms. We've got that, we know that. 2 tons of lime, what did that do? Well, it increased the pH, as lime should, but it only really increased the pH where you incorporated the lime. And so liming to, in this case, an average of about 5 to remove aluminium will remove aluminium, and that's great, but it doesn't allow the alkali or the pH increase effect to move down the profile. So at our lower liming rates, the lime doesn't move much at all. So it works where you put it and where you incorporate it. However, they also had this high rate of lime, and what the high rate showed was you get a bigger increase in pH because there's more lime there, understood. Where you've incorporated that, the pH is higher, understood, but you've also got a greater change in pH below the depth of incorporation. And so whilst liming to just remove aluminium won't create alkali movement down, liming to higher rates does allow movement. And at the time, it was a case of, oh, okay, well, high rates do it. You need a lot of lime, and maybe that's not economically viable, so let's leave it at that. But what we now sort of appreciate is these high rates of lime, what it's actually doing is getting the pH up and over 5.5, and that's a relatively important number, because what it allows movement of the alkali, and some of that's related to organic matter in soil. So components of the organic matter which change pH are more soluble and can move, and even the alkali product from the lime can move as well. So keeping a higher pH enables movement of alkali to depth. So that came from the 80s. Now, I want to show you what that means for us in our agricultural practice, and I want to, based on these little diagrams here where we've got soil pH on our y-axis and years of our management practice going from 0 to 20. Now, this is a conceptual example I'm showing you, but it's based on long-term trial data from the master trial, which was done not far from Wagga, and the data that supports this concept is in a paper under review authored by Guandi Lee and others. And so, yeah, we've got the data that demonstrates this, but I want to just take you through a conceptual example here of that, using some of the trends that data shows. So I've got 0 to 20 here, so it's going into the future, but the actual data was it's going back into the past. So we know what happens over a period of time because there was a long-term trial. They're good words. Rightio, so here we go. This soil pH by years, and I want to show you what that looks like in the 0 to 10 centimeter layer, and also what happens in our 10 to 20 centimeter layer. So same soil, just the very, very top soil, and then the 10 centimeters underneath that. And of course, you could go crazy and divide this up into smaller amounts, but conceptual, let's keep it easy. Rightio, so if you start off with an acid soil and you go, right, I'm gonna lime that, you add lime, pH increases, and then our agricultural practice, which is acidifying, will start to decrease the pH, and you'll get to a point where you say, right, I've reached my trigger point, I want to re-lime, I don't want my soil to acidify anymore, so I will put another liming event here. So add lime, increase the pH up again. And this might, it will depend on the soil buffering capacity, your actual soil, the type of soil that you have, how much lime you need to add. But this might be 2 tons per hectare of lime, say. So we add that, and then we acidify the soil again through our agricultural practice, and we reach our trigger point, we re-lime again. Okay, and that's going to give us an average of around about 5. That's going to take aluminium out of the solution, so we're not going to have an aluminium affected soil. We could grow sensitive plants there. The problem is, based on that Conyers and Scott data, we know that the alkali from that lime isn't going to actually get down below our depth of incorporation. This is assuming we incorporate. And so the acidity in that, or the pH in that 10 to 20 centimetre zone will continue to decrease with our agricultural production. So our system's getting worse. We're spending money, right? But we've still got this acidity problem at 10 to 20 centimetres. This is still our acid throttle, if you like. But it's lowered down, it's harder to fix. So, but we know if we keep that pH up over 5.5, then we have the opportunity for that alkali to move down into the 10 to 20 centimetre layer. So let's have a look at that. What if we lime to a higher rate? So let's do that. So our starting point's the same, but we lime to a higher rate, a higher pH initially, get it up over 5.5, acidify the soil with agricultural production, lime, increase pH, acidify, lime, acidify, lime. So this is the same, and if you like, this is like a maintenance, right? This is a maintenance liming event or liming strategy to maintain our pH, in this case, above 5.5, and in this case, at 5. So when I look at those, what I'm seeing is after 5 years, the cost is the same. It's, and the actual amount of lime might be a bit different, might be better in this case at the higher rate. But yeah, roughly the same. This maintenance is costing you the same here or here. But the big difference is this initial push to get your pH up over 5.5. That's the expensive bit, but it's once. The consequence of having this higher pH here in our subsurface soil, our below 10 centimeters, where we haven't incorporated it, but from the master data actually shows an increase in pH in the 10 to 20 centimeter layer. So that's over 10 centimeters. And so you imagine at 12, it's more. At 14, it's a little bit less than it was at 12, etc. But this is an average over that 10 centimeter layer. We've got an increase in pH. So what the situation on the left versus the situation on the right? The situation on the right is a system health improvement, and it's cost you, the only difference is it's cost you a little bit more in that initial liming event. Okay, so that's the concept. We've got some data from the master to support it, but that's one trial. Okay, so whether it's raising a flag here saying but or what if or maybe, this is one trial that shows that. We've got the trial from Conyers and Scott that shows the pH change, back in the 80s. So we're pretty sure it happens. How much, how fast is going to depend on the soil, going to depend on the acidification rates, the farming practices that are used. Okay, so there's more to know. There's more to know there for sure. But to me, that's it's a simple message in terms of the benefit to the soil. Complicated message in terms of economic benefit. I understand that. More work to be done. But if we don't have this line increasing, if we have this line decreasing, then we're just moving further and further and further towards a system failure of some sort because our soil's acidifying and deep. We know that if you do nothing, the soil acidity goes deeper and gets worse. And we've seen the data from history which demonstrates that doing nothing is not a good idea. Maybe a bit like climate change. Right. Well, what other options are available? Well, if you don't want to try to address movement of alkali lower by putting on that higher initial liming event to get the pH up over 5.5, then maybe you can place the lime deep where that acidity is in that 10 to 20 or 10 to 30 centimetre layer. And so we've got a trial led by Guandi at DPI here. I'm involved in it. We are others from CSU and partners at La Trobe as well, which is basically ripping in amendments. So we can put organic amendments or different liming agents down the tubes at 30 centimetres into that acid subsurface layer. But of course, takes a fair bit of horsepower to do that. So our work so far shows that yes, we can change the soil chemistry using that. That's fine. We get differences in crop yield at some sites, some crop varieties more than others. So it works. Is it economically viable? You know, that's the long-term question, I guess. But we've got to have the trial data to see how effective these strategies can be. So in my head, you know, if you're not going to put lime on the surface, you know, in the top 10 centimeters where it's easy to do, lime at a higher rate and incorporate. If you're not going to do that, eventually this will be your option to ameliorate soil acidity deeper in the profile, and this is more expensive, I think. Okay, so we understand acidity, what causes it. We've got that pretty well understood. Lots of people have spent a lot of time in labs and glass houses in the field understanding what causes acidity. Great work done in Wagga historically, Rutherglen, and over in the West. You know, there's been a lot of work done to understand the causes of acidity. The modelling enabled us to understand the causes, but it doesn't allow us to address the acidification in practice, because in the field, the soil processes occur in different layers. Plants grow through those different layers. And so we need to monitor the soil pH in our soil in different layers and through time to understand how our pH is changing as our farming system changes. And in doing that, we need to think about sampling a lot more than we have. We need to think about what depths should be used for our particular soils and where should we be taking those samples from. And so in those cropping contexts where we've got controlled traffic, we know we're putting the fertilizer in the same place. We need to think about that in terms of when we go coring. That should not be a random exercise. We should know we should be coring on those past fertilizer rows to see the effect of that pH in that row if we're worried about the acidification due to those fertilizers. There's a bunch of new technologies available to us in terms of sampling or data acquisition, which can be used to get a heap of information about soil pH and soil properties within your paddocks or paddocks that your client or that you're concerned about. To me, the big question is, how much information do you need to make a good decision or to have good knowledge? So what is optimal is a question. If you've got a heap of money and you just find the technology cool, well, you can probably never have enough information. But at some point, I think for a paddock, there's a point where people can waste money finding out stuff that doesn't actually help them make a better decision. And that's going to depend on the soil, the topography, the history of the sites. But there's a lot. I think there's a bit of thought to be had there, and I know there are people working on that too. So we're moving in that direction. But yeah, I think people need to think a lot more in that space. This subsurface acidity must be addressed. I think if we choose to ignore it, yes, you can grow acid tolerant plants or aluminium tolerant plants, and that's fine. But what that does, it just allows you to keep being productive on that site, but it doesn't stop the acidification. So eventually your system declines to a point where it's going to be very expensive to make it better. And I've had discussions with people and they say, oh yeah, but oh, we can't afford to do the sort of liming practices that you talk about, so we'll be right. And then, you know, if there's a crop option that's going to create a higher return, but it's not available to you because your pH is too low at depth, then that decision not to address the subsoil acidity has cost you a lot of money. So there's an opportunity cost for inaction. And so, yeah, I think we do need to address that subsurface acidity. At the moment, from what we've seen, it would make sense to lime over a pH of 5.5 as a target, but we really don't know what's the optimal pH. What, you know, is 5.5 the best? Is 5.8 the best? Is 6? We don't have the data to demonstrate that in terms of benefit to the farming system, benefit to the soil properties, and the rate of movement. So there's more work to be done. And if we've got acid soils and we want to do something about it, then liming, high quality lime, incorporating it works. Like the data is really clear on that, it works. If you don't incorporate, you're asking a lot of that lime sitting on the surface to change pH 10 centimeters down. Now that incorporation, it is not every year, it's just in the year that you lime, and so it might be 1 year in 5 or 1 year in 10 or somewhere along that, depending on how rapidly your soils are changing pH, and you'll know that by sampling and monitoring it. But work's been done. Mark Conyers did work here in strategic tillage at Temora, where you know, he showed that if you mix the soil, the damage in inverted commas that is done is short-lived, and you know, if you've got a higher organic matter in your soil, maybe from a pasture phase, it's really short-lived and pretty minor. So there's more benefits than negatives. That statement made, understanding that in some soils, due to topography, you can get erosion risk by incorporation. So we understand that. But in terms of changing pH in the surface soil, incorporation is definitely the best thing to do. And think about people that lime without incorporation and then soil test and say, my pH has gone up, everything's good, and then wonder why plants aren't looking so good when they're establishing. Maybe it's time to get a dig stick and a pH indicator kit and going and finding out whether you've got stratification, or do those sampling, smaller incremental sampling. So yeah, that's looking forward. We've got new technologies in our sampling and in also our distribution of fertilizer. We need to think about that. We need to do some work with that, and we need to understand how current farming systems are acidifying the soil. How quickly can we rectify that? So I'll leave it there. Thanks very much, everyone, and thanks, Abby.
Thank you, Jason. That was fantastic and a very good explanation of what the theory says and then what that actually really means in the real world, and what we can do with that information and all the new information that we're learning to manage soil pH. So as I said at the beginning, there's now time to ask questions of Jason or to pass some comment, and there's quite a few questions already. So I will launch into those and ask them from the top. There's a few comments from Neil Innes, who's talking about work in sugar cane regions and pH decline with the alleviation of placing superfine lime at various depths, like 20, 40, 80 centimetres, things like that. And he's also asked, what about the pH decline from growing legume crops that are ploughed in? The Central Queensland Coastal Farming Systems Project has found that legumes incorporated immediately drops pH from leaching of organic nitrogen to depth. Did you want to comment on that, Jason?
Yep. So yeah, thanks for that question. as part of our GRDC project, we've used loosened pellets, so a legume pelletized, so get it through our machine to put it at depth, and yeah, pH, it definitely makes the pH change quite a bit. Initially, you will get an increase and then a decrease, and so yeah, the processes that occur due to that organic matter addition, they're quite dynamic actually, and again, they will cause processes to occur at different spots in the profile. So whatever management practice that's being used, would be good form to monitor that through time, just to see what the effect is, because you can have short-term benefits in terms of pH, and then down the track acidify the soil again pretty rapidly. Organic matter per se added to the soil will always initially increase pH, because the breakdown of that organic matter is an alkaline process, but in doing so, it will release ammonium, which will then subsequently be either taken up by a plant or nitrified, which in both cases will be acidifying. But that may happen at a different place to where the organic matter breakdown happened.
Okay, thank you. There's quite a few questions around liming products and things like prilled lime products. So I'll ask you some of the, so there's some of the specifics around that are they useful when placed with seed at sowing? So Nerily Brennan's asked that. Andrew Kennett's asked about the use of fused calcium silicates as a soil conditioner or a liming agent. And yeah, are the prilled products better than ag lime and that sort of stuff?
Yep. So first, so let's just talk general. Yep. So basically, any product that's, if it's limed and then turned into a granule or a prill, there's been an extra production or manufactural component there, which is going to be an extra cost. So there's an extra cost there to add. So you've got to get a benefit from that extra that offsets that cost, and it's often your ability to how you apply that product is the benefit. And so I think, given our, like I mentioned before about the placement of fertilizers is quite controlled now, and precision placement of fertilizer, then that's where I think that those prilled components or the granular components are probably a really good tool to start to target the amelioration of the acidity formed in those sowing rows. However, I have not seen that researched as such. Like, I know people are doing it, but in terms of replicated trials, I haven't seen the data. I'm not saying it hasn't been done, I'm just saying I haven't seen it. So I can't comment on how effective it is. I know that if you sat down and you said, I've got a ton of prilled lime versus a ton of superfine lime, how you get that ton of prilled lime into the soil other than broadcasting, it becomes there's a practical issue there. There's an awful lot of product to stick down an air seeder, say. But I know if people have done it, they do it with multiple passes, and that's how they get that done. But also, if you're targeting a zone of acidity within a drill row, then you don't need perhaps to put on so much. So there's compromises to be had there. Andrew's question about the calcium silicates, I haven't done stuff with calcium silicate. We've done stuff with magnesium silicate, our prelim results have shown that it's effective at increasing pH. It's effective at getting rid of aluminium, and the effect of that amelioration is very promising in as far as having an impact lower than the depth of incorporation, more so than just normal lime, for example. But we need to do more work to understand why that is. But yeah, the calcium silicate or magnesium silicate, if the calcium silicate's behaving the same way as our magnesium silicate has, then there are benefits, especially in terms of how quickly alkali can move. Yes, it's promising for sure.
Okay, that's very interesting. There was just one point of clarification when you were saying that the ideal might be to lime to 5.5. Julian White wanted to know whether that was the pH measure in water or calcium chloride. I assumed it was calcium chloride.
Yeah, no, it's calcium chloride, Julian,
Yep.
because that work was done locally here, and all of our pHs we do in calcium chloride, 0.01 molar calcium chloride. Yeah, and again, like you would, that's just a measure. You could use different measures as long as you're consistent with whatever tool you're using to make your comparisons between management, treatment, if you like, and time. Yep.
Yeah, I think that's valuable. We have a question here from C. Dowling. I think it's Chris. And they've said, is there likely to be an effect of changes in rainfall distribution and quantity from apparent changes in season, like dry seasons, on the rate of pH change, given that it's a water-driven chemical reaction?
If so, is that one assumption is that we're talking about the liming, and the other one's just acidification, right? So I'm not sure which one,
I
but I'll
think it's
go with
probably
both of them.
acidification, but yeah.
Okay, yep. So yeah, it's for sure. Like rainfall matters. It matters in terms of how far things move, and that's a relationship with soil texture and cation exchange capacity as well as rainfall, and it impacts also on the productivity of that soil, and that's going to impact on the acidification rate. And for example, this year with the drought, whilst you might not have as much organic matter being produced because we didn't have a lot of rainfall, a lot of people are cutting hay and or cutting crops and carting out the entire crop above ground material out of the paddock. So the acidification rate, in theory, will still be quite high there. And again, you could model that, and that's fine, and you get an answer in terms of a bucket. But probably the best thing to do is to monitor the pH so that you can see what the impact of that was through the years, and then importantly, you can know how quickly your soils are acidifying and how fast or how much they respond. What's the magnitude of the response to the liming that you do for your soil? So it's a customized knowledge bank, if you like, for your soil.
Great. Yeah, I think that's valid. There's a couple of questions from Luke, Taylor, and Neil in this again about the liming products and superfine lime and prilled limes and things like that. Just, I think you've probably answered them, but if we haven't answered your exact question, Luke and Neil, if you could just let me know in that question pane. Simon Thompson has said, is there ongoing work being done to establish the ideal pH to lime to relative to alkali movement below incorporation depth over time?
Yep, so probably not. So the stuff that I presented there today, it's from a trial that doesn't exist anymore, but they're still publishing papers from it and still looking at the trends through time. So that's where that comes from. Yeah, there's historic trials out there that apply different amounts of lime. But yeah, we're doing work looking at how ways to get alkali at depth. So we're chewing away at that problem, but we don't have a particular trial per se where we've got a bunch of different liming rates and we're looking at alkali movement, if that answers that question.
Okay, and that might also, Luke's clarified the question that he was really after was about rates. So I guess that's what you've just said, that you're doing that work at the moment.
Yeah, so just on that, like remembering that table that came from alignment model, but it was a table output of that model. It's based on superfine lime incorporated at 10 centimeters. And so if you're not doing that, then you're not going to get that result, you know. So and it's not a case of, well, therefore I've got nothing, you know, we might as well make up a number. You still use it, but at the end of the day, the best thing to do is to measure your own pH and work out, okay, using that table, I should incorporate, and I should add, say, let's just say, you know, 3 tons of lime per hectare and incorporate it. And I've done that, and it was supposed to get my pH to 5.5, but it didn't. It's only got up to 5.3 or 5.2. Then all that means is, okay, your soil has a higher buffering capacity, so you need to put more lime on, or the lime that you used maybe wasn't of that same quality. Okay, so you can, that information that you gain then says, right, next time I lime, I know I need to put more than that out. Okay, because that particular soil has a higher buffering capacity. And without trying to get too complicated, you know, the amount of organic matter you have in the soil can change your buffering capacity. So you know, if you're coming in and out of pasture phases, it can have an effect also.
Yeah, I think that real take-home message then is that there aren't blanket sort of treatments, if you like, and because soil's not some kind of homogenized entity, that's why you need to do that constant monitoring that you talk about and really know your own situation. There's too many variables.
Yeah, and people will have that. People will have that from, you know, their region. If they're making a lot of recommendations, they'll have their own set of data that's creating their regional specific knowledge that will be able to define that probably better than a table anyway.
Yeah.
But
Vicky Bruns asked an interesting question. She says, do you think that soil acidity is the most important reading you would want to get in order to make an informed decision about the best way to improve your soil? That is liming the ultimate answer to soil management?
no, but like, it's close to my heart. But yeah, no, so I think, you know, it's true for soils, it's true for life. If you focus on one thing, you're going to miss something else that's really important as well, and that's not going to be optimal. So you know, it's a component. We know it. We know the system's sensitive to it, so you'd be crazy not to look at it. But if you only look at that, prepare for a rude awakening. Like, it's not going to end well. So it's one of the things for sure. But yeah, and in terms of my soil health, then you know, soil testing, and I should say too, when I'm talking about 0 to 5, 5 to 10, 10 to 15, people say, oh, it's going to get expensive. Like, I can't get people to have a 0 to 10, it's too expensive. You don't have to get everything measured. Like, you know, like if a soil test for the routine everything's is $100, $120, you don't have to get that done every time you soil test, because if you're concerned about pH and liming, the effect of liming on pH, then you can take 0 to 5, 5 to 10, 10 to 15 like depth increments, and just send them to the lab and say, I want pH measured, and that will cost, you know, $8, $10 per sample. That's cheap, you know. And so you don't have to have all the bells and whistles, but it's what you're looking for. And you know, at that time, given that you've sampled the soil, maybe you might look at Coldwell P as well, because it doesn't cost that much more. But those two things can tell you a lot. Your cation exchange capacity may not change too much. Your buffering capacity may not change too much. There's a bunch of things that people can measure that don't change frequently, so you don't need to analyze them frequently. But if you put lime on, you're chasing a pH change, so look for it, measure it. And just coming back to Vicky's question, like, in terms of soil health, take the sample, but dig a hole, find out what's underneath the area that you're actually coring as well, and have a look where the roots are growing. If they're growing all the way through, then that's an indication things are good. If they're not, why aren't they there? Why aren't the roots getting through? This year is a bit difficult because, you know, it's dry, the roots didn't get through because there was no moisture, but in normal years, like the fact that roots aren't getting through is an indication that there's a problem and you need to work out what that problem is.
I think also what you said before, there is a cost in not doing things. So maybe that's just a way of looking at it slightly differently. And perhaps that ongoing monitoring can be seen as a form of insurance, if you like. I mean, we pay for insurance for various things so that we can make informed decisions.
Well, yeah, that's right. And like I've stood in paddocks with people with that dig stick and you know, and a failed crop or near failed crop, and they look at it and think, gee, I wish I would have known that. If I'd known that, things would have been different. And in some cases, the difference would have been a cultivation, you know, so it's not, and the outcome would have been potentially massively different.
Yeah,
so yeah.
That's a good point. There's one other question from Brett Tonkin, and he said, I have a new dairy farmer client who found last year that he had a much better establishment with Italian ryegrass on a paddock that he had direct drilled compared to the neighbouring paddock that was cultivated. Approximately 20 days difference to first grazing. Can this be explained by the soil acidity depth curve that you've spoken about? A bit hard to tell with just that information.
Yeah, I don't know, but yeah, so cultivation versus direct drill, I mean, you get the mixing, we understand that. You'll get a little bit faster breakdown of organic matter, so that can have a nutrition effect short term that we know that makes a difference. And just depending on the soil too, sometimes you know, you can bring things to the surface as well, depending on how deep you cultivate. So how shallow your topsoil is. So yeah, you'd really need to see what that soil looked like to answer that question well.
And like you said before, have a bit of a dig around and have a look. Yeah.
For sure, yep.
Peter Beale has asked, what's the impact of soil carbon levels of 3 to 5% on the impact of aluminium in the soil, as this is typical of coastal dairy pastures? Good question, Peter.
Yeah, that is an awesome question. So organic matter aids the binding of aluminium, or it can how it reacts with aluminium in soils is influenced by organic matter. So yeah, we know that for the same soil at different organic matter, different carbon levels, you'll have different relationships with aluminium as you change pH. And we sort of understand why that is. And in that Lymet model, that sort of change in carbon, you would hope to see in a higher effective cation exchange capacity. But I don't know, off the top of my head, I don't know what sort of carbon values were in that model, like what soils they used, what the higher upper end of the carbon levels were. So I don't know how they relate specifically to your soils. But yeah, it is the higher organic matter you have the potential to bind up some aluminium with that organic matter. But it does depend on what pH you're at.
Okay, and I'm not quite sure if you've answered this already, but Rachel O'Neill has said she was, after some comments on variable rate applications of using various products applied in a broadcast rather than incorporated.
Yeah, so variable rate technology, so you know, you can do that for sure. You've got to make sure that the area of management, the pixels of, if you like, of management, the value that you've got for that area is actually the value of that area. So you need to think about how that area, each one of those little management grid cells has been sampled. And like I said, the more samples you have from an area of management, the more confidence you can have in the numbers that come back from that. Yeah, and then it just depends how variable the soil is. But I always worry, my concern is with variable rate lime application is it's based on a pH value that's come back from however it was sampled. So the sampling is the key part. Is the number that you've got for your area of management representative of what's in that area of management, or is it just a number from within it? And that kind of, I think, determines how valuable your variable rate technologies are. Yeah, and then at the end of the day, if you broadcast that and don't incorporate it, I would say the value of all that work is probably minimal because your lime's still sitting at the surface. That said, that comment relates to in a situation where you could have incorporated if you wanted to, but you choose not to. Understanding that there are some places where you can't incorporate due to erosion risk or access.
Okay, we're almost at 11 o'clock, so I might call it quits there. I think that we have answered everyone's question. If not, just let me know because I could pass those on to Jason again. Just to also draw the attention of those people that are still here, that if you did want some basic info about what soil acidity is and soil pH and things like that, I've put two web links in the comments section, and one is a nice little animation from the Victorian government about why soil becomes acid or the pH drops, and the other one's just a link to the publications page from New South Wales DPI and the publications there that we have on soil acidity, including some of that master information that I think Jason spoke about earlier.
Yep, and our deep amelioration, subsoil amelioration stuff's there as well. Yep.
Great. Yeah. So that's a good place to keep looking, and we are actually looking at updating. There's a fairly ancient ag fact called soil acidity and liming that we're looking at updating to put some of the information that, or all the information that Jason spoke about this morning into that to give a better picture of what we know about how things work now. So I would just like to thank Jason very much for that presentation. As I said, it was really great, and thank you all for attending. And next month will be our last one for the year, and we have Susan Orgel presenting, so look out for that invitation. So thanks very much, Jason, and thanks, Luke, for hanging out there in the background.
Thanks, Heavy.
See ya.